Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and we're going to focus our efforts, essentially concentrate on the idea of stellar death. And remember, stars are not alive, but they do really end their existence as if they're creatures that die after a period of time. And what we'll find out is that how the star goes through this process of stellar death is, of course, always related to the mass of the star. The gravity that the star has will be part of how the star deals with a variety of crises that the star will face. So let's go back to our picture on the right here. The sun, at the moment, is somewhere right about in here. If each of these dots represents a point in time, just a regular time interval, our sun is a very middle-aged star that is producing energy at a steady rate, not terribly excited. The star is not an exciting thing. It doesn't change dramatically day to day, and that's a good thing. If the sun were to dramatically change from one day to the next, producing more energy, producing less energy, that would be a crisis for life on Earth. We wouldn't survive that. So the sun is very mundane, and it's going through its main sequence existence about halfway through its lifespan. But what we know is that the sun can't maintain this forever. At some point, the sun is going to go through some very dramatic changes. And when it goes through these dramatic changes, that will be the end of life on Earth as we have to deal with these changes. We won't be able to deal with those changes for very long. And the Earth will actually have quite a few things to have to deal with the changes of the sun. We'll talk about that in another video. And in the future, the sun will change very dramatically into some object that will be what it ends up being for the rest of its existence. And we'll get to that as well. But what we're going to talk about today is, in this video, we're going to talk about those beginnings of the transition, the stage of life where the sun is transitioning into a different object because of a few things happening in its interior. So let's talk about that. At the beginning of the life of a star, it doesn't matter what the star is when it comes to its mass. It could be a low mass star, could be a medium mass star, it could be a very high mass star. It doesn't really matter. All stars start off with their chemical composition being almost entirely hydrogen. If you remember in a previous video, we talked about how the universe is primarily made out of hydrogen. About 90% of the universe material, the stuff of the universe, 90% of it is hydrogen gas with a small amount of helium. So the star begins with its chemical composition being almost entirely hydrogen. And in a previous video, we talked about at the core of the sun is where the nuclear reactions are taking place. So I'm going to re-emphasize the idea or the concept behind the word core. Remember that when we refer to the core of a star, we're referring to the region that the conditions for nuclear fusion are possible. And remember, those conditions are very high temperature as well as very high pressure. So deep down inside of the sun, where gravity is really bringing all of the material of the sun to a point, gravity's trying to crush the sun down to something very small. At the center of the sun, the temperature is 15 million kelvins, and the pressure is 3 trillion pounds per square inch, and that allows the hydrogen to fuse into helium. But if we get away from the core, if we go further and further away from the core, closer to the surface, the temperature of the sun goes down. It's hottest at the core and coolest on its surface. The surface of the sun is about 11,000 degrees Fahrenheit, which is about 6,000 kelvins. The center of the sun is 15 million kelvins. And so the temperature difference is dramatic. And the problem with that is when you get away from the core and the temperature slowly drops, you reach a boundary where fusion is no longer possible. There is no pressure high enough to make the hydrogen to fuse. The temperature is not high enough to cause the hydrogen to fuse. And so the fusion will not occur anywhere that is closer to the surface than this boundary. Now, the reason why I'm going through that is because this brings up a term that we're going to use quite a bit in the next several videos, and that is the word envelope. Just like a letter is surrounded by the envelope that you mail it in, Every star's core is surrounded by a region called the envelope. And the definition of the envelope is all of the material of the star where fusion is not happening. So this hydrogen that the star is made out of is very hot and the pressure is high. It's just not hot enough, and it's not high enough pressure for fusion to happen. Remember, hydrogen takes a very high temperature to make it do what it's trying not to do. And so the envelope of the star is hot, just not hot enough. So every star can be divided into two regions: the core, surrounded by the envelope, and of course that reaches the surface of the star. Now the reason why I mention this is because when the star forms, when our sun formed or any other star forms, the core is mostly hydrogen. But what's going to happen is, as every day and every week and month and year and many, many years goes by, this core is steadily being turned from hydrogen into the element helium. And so halfway through the lifespan of the star, half of the hydrogen has been converted to helium. Think about how the quantity of hydrogen is going down and the quantity of helium is going up. But by the end of the star's existence, what's going to happen is the core is going to be transitioned entirely into helium. The fusion of hydrogen into helium makes the core become helium, surrounded by an envelope still made of hydrogen. So the future of any star, as we start to get towards the end of its existence, the future of the star will be one where its core will be turned into helium and the envelope is still hydrogen. Every star will face this problem, whether it's a low mass star, an intermediate mass star, or a high mass star. The problem is always what happens when the core becomes nothing but helium and it is still surrounded by hydrogen. The problem with having a helium core is that the element helium, although it is capable of fusing into another element, the element helium requires a higher temperature than hydrogen does. So let's have a look as to why this is. Let's go back to this frame from a previous video. This is, again, the proton-proton cycle. Remember, 4 hydrogen nuclei fuse to become 1 helium nucleus, and out of which you get 2 photons of gamma ray light. If we look back at this, here's the problem that we had to overcome to get the hydrogen to fuse. These 2 protons, 1 proton by itself is a hydrogen nucleus, but the protons are positively charged. So the electrostatic charge of a proton is positive. And if you remember the rules of science, when you have 2 positively charged particles, they repel each other. In other words, you get 2 positives or 2 negatives. If they're like charges, then they will repel. And so what we saw in a previous video is to get the hydrogen to fuse when it's trying to push itself away from itself, what we have to do is overcome that with a very, very fast speed to make the collision unavoidable. So if you make these move fast enough, they're forced to collide, they're forced to fuse, and we get eventually the fusion of hydrogen into helium. But to force this fusion reaction to occur requires a minimum of about 2 million kelvins for hydrogen. So hydrogen requires this minimum temperature to overcome its electrostatic repulsion. The problem is once we have helium nuclei at the core, you'll notice a helium nucleus now has 2 positively charged protons. So getting helium to fuse with another helium nucleus, we have a greater electrostatic repulsion because we have more protons, each of which is positively charged. So helium has a greater resistance when you push it next to another helium nucleus. The second problem is a helium nucleus is actually very heavy compared to hydrogen. Hydrogen is 1 single proton, helium is 2 protons, now with 2 neutrons. So the mass of helium as a nucleus is heavier or more massive than hydrogen is. When you put those 2 together, 2 million kelvins is not hot enough to make helium go fast enough to fuse with other helium nuclei. It's sufficiently hot enough to get hydrogen to fuse, but it's not hot enough to get the helium to fuse. So the problem is when the core of the star turns into the element helium, the temperature of the star is no longer hot enough to get the helium to fuse. Remember, what made the star hot in the first place is the gravity of the star. We haven't changed the mass of the star. So if it started off at a couple of million kelvins, hot enough to get the hydrogen to fuse, when it develops a helium core, it is still a couple of million kelvins, and that's not hot enough for helium to fuse. So what happens is every single star in the universe will face its first crisis when it runs out of hydrogen at the core, develops a helium core, and then is no longer hot enough to get the helium to fuse. And if you have helium at the core that's not fusing, then you have shut off the nuclear engine. So the star is no longer producing energy, and if energy isn't coming out, then hydrostatic equilibrium is gone. Surprisingly, the sun will only use about 5%, just shy of 5% of its total amount of hydrogen when it has converted that hydrogen to helium. So what this is saying is after 10 billion years of existence, about 95% of the sun's original hydrogen is going to essentially never be used. The sun will use slightly less than 5% of its total hydrogen. So even though this process lasts for 10 billion years, just a small amount of the sun's hydrogen gets turned into helium because that's the hydrogen in the core. All of the hydrogen in the envelope is just in the wrong place. It cannot fuse, and if there's no mechanism to bring that hydrogen into the core, the sun will die with about 95% of its unused hydrogen still sitting there. Now what we're going to do is we're going to begin this discussion of how do the stars deal with this helium core. In other words, the crisis that the star will face is that it has developed a helium core and the nuclear engines are starting to shut off. How the star deals with that depends on its mass. You'll notice that we've taken the main sequence and we've broken it down into 3 sections. And each of these sections are related to the mass of the star. This is the section that is the lowest mass stars in our universe. We're just going to simply call these low mass stars. Stars that are higher in mass, but still fairly intermediate, obviously, we're going to call intermediate mass stars. And then we're going to talk about high mass stars. So essentially, there are 3 versions of the death of a star, and each version is slightly different based on the mass and how the star deals with this crisis that the star faces. So ultimately, the stars of our universe, they're all going to die. They're all going to end their existence. They're all going to die for similar reasons. The running out of their fuel at their core and developing a core of a new fuel that is just at the wrong temperature to be able to do anything with it. And what we will find is that gravity is still the driving force, and the mass of the star and how that star deals with this crisis is going to be, of course, related to gravity. So we're essentially going to embark on a story that has similar components to it, but 3 very different outcomes based on the masses of the stars. And we'll begin that discussion of stellar death in the next video. I hope you'll join me.